So I once again welcome you all in this tutorial session where we will be covering about the advanced manufacturing of the material. So in this lab we have 3D printing setup, right? That is generally used for the part fabrications. Either you can use polymer or you can use polymer composite as well. Okay. So here this is DLP machine. This is small one. Now means in the coming month I think means more DLP machines will be available here because file is under process. But this small one is very useful for us. So we are using it I think since last 3 years, and we have made a lot of parts. So here you can see that here these are the components which we have fabricated through this DLP process. Right?
This is injector type.
Yeah, because we are also working on the other projects, right? So for that purpose, we have made this extruder head. Okay, so we have added this nozzle, and you can see the quality, right? You can see the quality and finish that we have obtained through this DLP. See the surface finish, because most of yesterday I was talking about the post processing, right? Why post processing is required? Sometimes it is required to finish the surfaces, but here in DLP you can get very good surface finish and you can minimize the requirement of post processing. So this is one advantage with DLP. Okay, and here okay, keep it here. So and this is the FDM printer, right? And here we can process material in the filament form. Right? If you have any polymer composite or any polymer, and if you are able to convert that polymer into filament form, then you can use this machine. Okay? Because here filament itself acts as a plunger. Do you know the principle of this? For extrusion, either we use screw extrusion based technology or we use plunger based technology, right? But here we don't have any physical screw. And on the same hand, we don't have any plunger-based mechanism to process the material. Then how we are able to extrude the material? My question is this: how we are extruding the material? We don't have a screw-based mechanism, okay? And also we don't have the plunger-based mechanism.
You spraying it?
No. Right. Because here what happens when we feed this material in the filament form? Wait, please switch on this. So what happens when we feed the material in the filament form, and filament goes inside this extruder head, right? This is the pipe, okay, through which this filament will enter into the extruder head. So this filament, solid part of the filament, will act as a plunger itself. So that's why there is no physical plunger inside the extruder head, right? So by that mechanism or with the help of this principle, we are able to extrude the material in the thin wire form.
This must be hollow.
No, not hollow, sir. Hollow, basically this is hollow. This is solid filament, right? This is solid filament. This will act as a plunger because when it will go inside the extruder head, here we have heating mechanism, so it will melt down, right? The temperature of this filament will raise up to, for example, 200 degrees centigrade. So we have two sections. One is the solid section, and on the bottom we have melted section, right? So that solid part of the filament will act as a plunger because we are continuously pushing this filament inside the extruder head. Okay, so that's why it is very simple, right? It's a very simple mechanism. When this was invented by statisticians, so they use this technology only. That's why this technology become very popular because it's simple to operate, simple to use, very simple mechanism. Only heaters are required, just right. One motor is required to push the material. So if you guess the cost of this printer, it is available only for 12,000 rupees, 30,000 rupees in the market. If I talk about the laser-based mechanisms, they are costly because laser itself is very costly, the power source. So today we will show you, suppose if you have any material with you and if you have converted that material into filament form, how can you prepare the specimens, how can you prepare your functional parts using this process and using the FD process. So this is basically the objective of this tutorial session, right? So those who do not have any idea about 3D printing, they can, that will be the new thing. Okay, this particular technology will be a new thing for them. But those who know about 3D printing, this is very basic, right? But still some new information maybe is given to you. So here I am having this Vivek with me. So he will just show you. Vivek, just go there. So what we have done basically, we need to use some software, right? A separate software is required for DLP, right? And we use separate software for FDM. So initially, this is the Cura software, right? Cura software. Cura basically is a nicer software for FDM, right? So what we do in this, because yesterday I have just spoken about the 3D printing process change. So where from we start? First we make CAD model, right? CAD model. Then we convert CAD model into STL file. Then STL again is processed, that is sliced. Then we generate toolpath. So in this software, we will import the STL file. Then we will process that STL file as per our requirement. What is our objective? If my objective is to make the just a prototype of the specimen, I will change the parameter. If I want to make the functional part, I will change the parameter. So now Vivek will tell you how to use this. We will just demonstrate the software to our participants.
So from basic CAD modeling to slide.
Yeah, not just show the CAD modeling. Sir, do you have the idea of CAD modeling, everyone? CAD modeling. I think most of us from the mechanical background, so everybody knows. We'll start with the STL file first, right? And one more thing that I want to add. Here we have developed our own setup, right? That we have not purchased from the market. So we are developing it basically. It is under development. Yesterday I have shown you one part, right? That was having the continuous fiber. Continuous fiber. We integrated that continuous fiber inside the region. Where is that part? No, that part. Yesterday we have shown.
Which sir?
That continuous fiber one. In the meantime, you just prepare the software. I will just insert it then. Yeah, thank you. So yesterday I have just shown you this part. So you can see that here what we have done, we have used fiber in the continuous form, right? But in general, what happens? Generally we use chopped fiber and resin, right, to develop the polymer composite. Okay, that is normal, right? But here what we are trying to do, we are just trying to impregnate the continuous fiber along with the resin, right? So we are processing material in the liquid form and simultaneously we are adding this fiber. We are depositing both the materials, continuous fiber and resin. So we are just developing this machine under the CRG project. So soon I think it will be developed and then we will use it with the robotic arm. So robotic arm is under installation. The installation of this robotic arm is ongoing. So we will soon try to mount the setup on robotic arm. Okay. So this is also one of the machines that we have developed in our lab.
So robotic arm will print this.
Not robotic arm will print this because we are developing a extruder, right? That will have the capability to extrude that continuous fiber and epoxy resin. Then that extruder will be mounted on the robotic arm. This is the main objective of the project, right?
What is your objective to do this?
Sir, I cannot disclose right now, but I will tell you. Okay. in the simple way I have just explained what is the objective. Yeah. Right. So now just focus on the screen, right? So here Vivek has taken a tensile specimen, right? So tensile CAD model, suppose he has developed in the CAD model software. Now that STL file has been imported in the QRA. Now just zoom it. So when you just import this STL file in the software, it automatically plays on the print bed because we have already selected the printer type, right? So we have selected this printer in the software, so it will automatically fetch the information. What are the process parameters of this printer, right? That can be monitored or that can be varied. Second thing is what is the exact build size of the platform, because this is standard printer that is available in the market, right? So here what he has done, he has imported that STL file, and now he will process the STL file. So what kind of processing will be required? See, I can print my STL file either in this orientation or in this orientation, right? So by using my own knowledge, my wisdom, I will decide the orientation of the part. And how I will decide? Based on my requirement. What are my requirements? Whether I want to focus on the aesthetic look of the product or I want to focus on the strength of the product. Accordingly, I will select the orientation. So we will just change the orientation of this specimen first. So suppose he has selected the part. Now what he is doing? He is changing its orientation. Now, okay, just press OK. Now its orientation has been changed with respect to the build platform, right? Earlier it was in the horizontal orientation, but now its orientation has been changed to 90 degrees, right? 90 degrees. So according to the requirement, we can change the orientation, right? According to the main requirement of the product, we can change this orientation, right? Now, once you finalize the orientation, okay, see, orientation is very, very important. Why? Because number of layers, how many layers will be there, it will depend on the orientation. Because earlier, the whole part was oriented in X and Y direction. Okay, so that time, height of the specimen was only the thickness of the specimen. Let's say 6 mm, let's say. And suppose I have opted 1 mm or 0.4 mm thickness, slice layer thickness. So how many layers I need to add to complete the fabrication of the sample? 0.4, 0.4, 0.4, so 1.2. Again 3 more layers, 2.4. Again 3 layers, 3.6. So what I told you, the specimen thickness is 6 mm. So now you can calculate, right? How many layers will be required? If you change the orientation, right? If you rotate the specimen by 90 degree, what will happen? The height of the specimen will be increased, right? Now, because he has changed the orientation of the specimen, now height of the specimen has been increased. Now more layers will be required. Okay, but we should try to keep it minimum. More joints, we should avoid more joints within the specimens, because our object is to make part with adequate strength, right? Adequate surface toughness. So we can decide the specimen orientation by just using the wisdom only, okay, and requirement. So operator will decide. Okay, just flip it again in the same condition. Yeah. So again here change the orientation to the 0 degree. Okay, orientation is the position of the specimen with respect to 3D space, with respect to the volume, right? Build volume. So now again the orientation is in the XY direction, right? Now we will move to the next step, that is slicing. So slicing means, because as I told you that additive manufacturing is a process where we fabricate three-dimensional object by adding the materials in the layer form. Right? So slicing is required to just identify the number of layers required to fabricate that particular specimen. Okay. So now you slice it. So again in the software we will slice it, and then see, we have sliced it. Now zoom. Have you generated toolbar? We will?
Yes, sir.
Okay. So on the same time, he has also generated the toolbar for this particular specimen. Okay. After slicing, right? Now you can see the simulation. Now nozzle is moving along the different direction to deposit the material. So currently you are having okay. So this is base layer, I think. Yeah?
Base layer.
First layer. Huh?
First layer.
So first layer. So the nozzle is moving, and when it will move to the second layer, just focus on this the pattern. What will happen?
Second layer.
No, it's okay. Now just focus on the pattern, right? Now what is happening? At 90 degrees, right?
Crisscross.
Crisscross pattern. Actually, he's forming the software is forming the crisscross pattern to increase the contact, right, between two layers. Okay, strength between two layers. So again, third layer, again orientation of the pattern has been changed, and for the next layer again
We can change this orientation.
yes, this orientation also you can change, but I don't think in the software this
We can change it.
okay, this feature is available. Okay, we can change this orientation. Okay, we can decide what pattern you want to use for that particular layer, so that is changeable. Okay.
So, sir, height is 3.2 and layer thickness
So the
is
actual height is 3.2 mm. So
And
what layer thickness you have?
0.1.
0.1 layer thickness he has opted.
So 32 layer.
So total number of layers are 32, right? So this nozzle will divide 32 layers, and we will print this specimen. Okay, just download toolbar and upload on this machine, right? So now what we are doing? We are going to save this toolbar, right? And we will take this toolbar in the pen drive and we will upload on the machine, right? So this is also one way to transfer the file. Or else we can connect the PC. Correct? Connection we can even establish just to transfer the file into the machine, right?
So it has the hardware for that file to process.
Yeah, it has. It will automatically read the pen drive and it will ask which file you want to select or the part of division, and then it will store. Yeah. Here we have two rollers, right? So they will rotate like this, and they will push the filament inside the extruder head. This is PTFE tube that will assist the filament. Okay, so it will go inside the extruder head.
We have flexible bed also, sir.
So this is flexible. Later on we will show. So we are just printing this specimen just to demonstrate the capability. And if you want to try, you can also try, right? If you need any toolbar by using that software and you want to print, you can.
So these are the variety of materials we have over there.
So we have ABS, we have ABS conductive, we have PLA, we have the TPU also. TPU basically is flexible polymer, elastomer. So that you can print because you want to have some flexible properties. So you can easily make through this. Then PVA is sort of the water soluble material. Water soluble, right? Suppose you want to use a support material, right? And that should be water soluble. So you can use PVA. So long back you can purchase this. And under resin category, I have acrylic resin, epoxy, and you can see the list. So we have a lot of things. to prepare the composite also. Like suppose you want to work on the conductive composites. So in that case, you need to add the CNT, carbon nanotubes, right? Or sometimes you need to add the graphene also. So those things are available because my scholars are exploring this area. So they develop their own material and they just check the printability of that material also. Right? So we have published these papers only this year. In 2024, we have published almost 10 essay papers of this line only. Right? So so start also. No, because once the part printing is completed, right, we need to remove the specimen from the base. So if it is not flexible, then what will happen? The first layer is stick with the platform, and it will be very difficult to remove that base layer. So it will damage the part also. It will damage the printed specimen. So now what we do? We just take out this print bed in our hand and just be bend like this, and then automatically that thickness actually is removed, and we can easily remove the specimen from the print bed. So this is, I think, one of the advantage. But earlier when I was I started this 3D printing in 2014. So that time only fixed bed was available with the 3D printers. So that time we used to use some tools to remove that sticky layer. That time sometimes the parts were damaged, or sometimes the part failure were also occurred. So that's why nowadays these printers have the flexible beds. Okay. So now what is happening? Because we have loaded, so we have loaded the file, right? Now what is happening? Because it has automatically read the instructions which we have uploaded. So in the instruction somewhere the temperature is 200 degrees centigrade. So because it was in the switch off mode condition, so temperature of the extruder was 20 degrees centigrade. Let's assume, considering the cold condition in Jalandhar. Now what is happening? The heaters are switched on and they are just increasing the temperature of extruder up to 200 degrees centigrade. And similarly, base heating also we have provided to the instructions, right? So now if you touch the bed, you just come and touch the bed. The temperature of the print bed has also increased to the 50 degrees centigrade or 60 degrees centigrade, right? So now it started moving, right, along X and Y direction. Sir, more printers are actually in pipeline, and I think by the next week I will have the Bamboo Lab multi-material 3D printer in my lab, right? So that printer has capability to deal with 4 materials. Yesterday I discussed about this printer. So that Bamboo Lab printer also I have purchased. So that will be available, I think, in coming weeks. I think by the end of this December. Okay. So restart again, I think, because so this spool actually material comes in this form, in the filament form. And yesterday I talked about, if you are planning to make any composite material for FDM process, what you need to do? You need to ensure the diameter. So diameter should be 1.75. Vivek, can you give me that vernier caliper? So let us check the diameter of this filament, right? See, right? See the diameter. Now it is exactly 1.75. So if you are planning to make any material, right? Any composite material, suppose you want to blend the PLA with any other filler material, you have to ensure the diameter. Otherwise, what will happen? Because the hardware will not support your filament, right? because hardware has the openings, right, and the pipe diameter according to this one only. So that is why it is very difficult, right? It is very difficult to print composite through this FDM.
Sir, what happens if the diameter will be less?
Less, in that case, the gap between roller, that is exactly around 1.7 mm, for example. If it is too less, 1.5 mm, the rollers will not be able to push the material inside the extruder head, because there will be no contact. If contact is not, not between the rollers and filament, then it will they will not be able to push the filament inside the extruder head. If it is too high, then also same thing will happen. You will not able, even though feed the material.
So there is no system that that extruder means that roller may adjust and push.
No, there is no mechanism. No.
Now,
as of now, there is no mechanism, right? But if you can, propose a new mechanism, if you can explore this area, then I think it will be a new domain of research, and you will add new thing into the 3D printers. So keep it. So now just see, because we model this specimen there, right? Now what is happening here? Nozzle is depositing material, okay, layer by layer. So once one layer is completed, nozzle lifts toward the Z directions, right? Toward positive Z. How much distance? By how much distance? 0.1 mm, because the layer thickness is 0.1 mm. That's why we are not able to see it by the naked eyes, right? 0.1 mm. So we are not able to judge when it is going to be in the upward direction or the downward direction. So this is another tool, right? So that is used to remove the part from the sticky band. Earlier it was made of metal, but now it is also, we have changed the material from metal to polymer. Metal, this is metal.
Previously it was.
You can focus here.
Can we know what is the time?
So what time? So already they have mentioned in the software. You by playing with the parameters, you can either increase the time or you can reduce the time. Suppose if I decrease the infill density, where currently I think where have you used 100% infill density? 100%. Because we have selected 100% infill density, right? Because we want to test the specimen. Because we have modeled the tensile specimen, and that specimen will be used to test the strength of the material. So that's why we have given 100% infill density there, right? But if you want to reduce the density, just reduce the density. Just show the consequences. If you reduce the density, what will happen? Just Vivek, what is the current build time for this specimen? 11 minutes. Okay. Currently build 100% infill density. The build time will be 100 minutes, right? Okay, 100 minutes. But when you reduce the density, the time will reduce to the 5 minutes or 6 minutes.
So this is the reduced density and reduced to 4 minutes.
4 minutes. Only 4 minutes. So this is, I think, one of the advantage. Tomorrow we have, I think, tutorial session on the material processing. Can you just check schedule? Do you have schedule? Tomorrow we have the one tutorial session on hands-on lab sessions for manufacturing techniques and material characterization, right? So here what we are planning, because I will Okay, we have one filament extruder with us, right? This is right? Yeah, this one. Sir, tomorrow we will try to make our own filament, right? This is one of the extruder screw based extruder. So this extruder will be used to generally it is used to prepare the filament. So suppose you have prepared the composite. Now when you feed that composite in this extruder, it will give you filament. It will convert your material in the filament form. So this is the manufactured by this film, right? So we have arranged this only for you. So tomorrow we will have the hands-on session. We will try to convert the pellets into the filament form. Then we will try to print that material only. Okay. So right from the pellets. These are the pellets. So we will try to convert these pellets into the filament, and then we will try to print the filament through the okay. And also we have the ultrasonic this on the back side, right? So this is very good instrument when you want to disperse the filler material in the matrix. Then this can help you in that. Okay. So we will see on tomorrow how can you use this particular instrument for that particular mixing or homogenizing the filler material with the matrix. Okay. So these two instruments I will try to demonstrate on tomorrow, right? Yeah. So that's fine. I will tell you the whole story. What are the use of this, right? And I am also having the magnet stirrer with me. So both things I will explain to you. Then we will come to this instrument. Then we will go to that. Similarly, for DLP also we will try to develop the composite, and for FDM also we will try to develop the composite. So कल ना एक थोड़ा region में कोई थ्रेड डाल के हल्का सा ज़्यादा नहीं कंप्लीट हो जाएगा इस थ्रेड करेंगे हमारे पास क्लियर का एक पार्ट नहीं कल लाइव देखा ना हैंड्स ऑन लैब सेशन है दैट वी विल ट्राई टू डेमोंस्ट्रेट राइट.
नॉर्मल पार्ट्स फ्लेक्सिबल है और इसमें ग्लास माइक्रोस्फीयर ऐड करने के बाद ये ग्लास माइक्रोस्फीयर ऐड किए गए और उसके अलावा रॉ ये सबसे जो रॉ ग्लास
कितने लेयर बचे हैं?
What we wanted to, why we wanted to make this composite, I think increase the dielectric constant. To reduce the dielectric constant. I will also tell you the story behind it. Okay. Why we have developed this and for what purpose we try to develop this composite. So tomorrow we will see. अभी आज यहाँ पर भी और टेक्सटाइल में भी है ना हाँ how much time is that? Just stop it.
95%. 95%.
95? मैं यहाँ फर्स्ट ईयर हूँ सेकंड ईयर में
4 years.
मेरे 5 साल हो गए मैंने भी 2 डिग्री लिया था आपका तुम्हारा 30 घंटा बढ़िया बढ़िया तुम्हारा की शॉप कितना कंटिन्यूस फॉर्म है तुम्हारा बता मेरा कार्बन फाइबर है उसके मटेरियल से लगभग सेम है मतलब स्टडीज वगैरह अलग है
सर
मेरा प्रोसेस डेवलपमेंट तो बात करेंगे बात ठीक है so now remove this specimen give it to me so sir now this part fabrication is completed, right? So now we have to remove this part from the print bed. So now you can check. We have successfully printed the specimen which we have modeled in the software. So what we have done? We have just converted our idea into reality. If you go through the injection molding route, then suppose you want to fabricate a tensile specimen, right? Through the injection molding process. First you make the program, right? And that program will be loaded on CNC machine. Then CNC machine will cut the material, and then we will prepare the mold, right? Then we will just load, or we will mount that mold on the injection molding machine. Then we will feed the pellet material. Then we will heat the material. Then we will press the material inside the mold. So can you imagine the time? But now we have reduced the time, right? So this is one of the main advantage of 3D printing. Isn't it? So this is the benefit. So similar to polymer, you can also use, I think we have one filled polymer filament, any conductive filament?
Conductive filament.
Just take it out. Similarly, suppose you want to process the composite material, polymer composite material. The same process, same steps will be followed, right? In the market, there are some manufacturers who makes the composite filaments as well. Composite filaments. Because this is simple normal PLA material, right? We purchased one ABS conductive filament from the market. Okay? For some purpose, right? But if you want to, you are doing research like us, then you can also make your own composite material. So do you have any sample with you? Your sample?
No, sir.
No? He has actually yesterday he has successfully given his open seminar, and he is going to submit his PhD. So what he has done? He has developed the conductive filament, right, for heat exchanger applications. Heat exchanger applications. So he tested those heat exchangers. He analyzed those exchangers for their heat exchanging properties. So he did a lot of analysis and the characterization. So he did very beautiful job for research. He has published, I think, 3 essay paper in 3 years. Part time, in 3 years he has completed. Right? So you can make your own material also. But first of all, you need to find out where you want to apply that material. What will be the application of that material? Then only you can select the matrix material and the filler material. Clear? Pause for DLP. Vivek? Okay, leave it. Come.
G2 box. G2 box is the software name. It is an open source software. So G2 box basic. G2 box basic is the free software, freely available. You can download it. G2 box Pro is there. You have to take the license. So we have G2 box basic. You can upgrade it to Pro just taking the license. So basic is free version. This is the interface of the G2 box, similar to that Cura software. We have to import the STL file from there. This is the build plate of that DLP. That one DLP build plate is there. It is showing in the reverse. So this is the part we have imported. This is the STL file, same dog bone shape we have imported in the G2box software. So see, this FDM 3D printer has a minimum layer height we can achieve 0.1 mm, but this DLP 3D printer we can achieve layer height of 0.01 mm. Means 10 micron layer thickness we can achieve. That is why surface finish of the DLP 3D printed part are very smooth over the FDM process, means FDM 3D printed part. This is the part we imported.
Here you can sit down, yeah? You can sit down here.
This is the part we have imported. Now slice setting is there.
So similar to the Cura, we have slice settings. We can choose parameter, we can choose resolution, right? We can choose the lot of things are there. So you can just see. You can select the machine also. Similar to the Cura.
In the Cura before slicing we have to select the 3D printer. Like here is Creality Ender 3 Pro is there. In the Cura we have used. In the G2box we have machine Photon Ultra. So Photon Ultra is there. Any cubic Photon Ultra machine is there. That is name shown here. We selected that machine. Then we have to select the resin, which kind of resin is here, resin density. It can also calculate the fabrication cost also. If you give the resin means cost, gram per ml means volume of the cost per liter of that resin. So in the print setting we can see the layer height, that is the layer height. We can go up to 0.01 layer thickness, and initially just the resin has to stick with the platform. So that is the bottom layer count. How many layer we have to make so that the resin can stick to the platform. Okay, so the count number is 2, and exposure time, how much second the UV light should be fall on that layer, that is 10 second. 10 second is the normal exposure time. For bottom exposure time it is 35 second. So this one is the bottom lift distance. After printing a single layer, the means platform will lift upside so that the liquid material can fill means in between the platform and the base material, because liquid has a density also, means viscosity of around 150 cp centipoise. If the viscosity is high, you have to lift the platform little higher so that it can take the high viscosity material will take more time to fill the gap in between the platform and surface. So 5 mm is the bottom lift distance. If we increase here to 15 mm, you will see the each layer printing of each layer. So bottom lift distance 15 mm, lift distance is also 15 mm. Now we apply to the setting. All the rest setting are means by default. Now it is saying that do you need any support, because removing the part in the FDM process it is easy, flexible material, you can remove the part, but this platform is a metal surface. It is very difficult to remove that resin from the platform, so you need that support, but the support also take much time. So here we won't take the support of that here to reduce the time only, but in actual part printing we have to take the support. Now slice at the 0.1 layer thickness. We got 2 hours 19 minutes print time.
2 hours 19 minutes. Huh?
19 minutes. It is based on the each layer.
Because they are
Like
very small, right?
the specimen, same specimen we are printing with FDM, we have printed that dog bone shape.
In 12 minutes, but it will take around 2 hours.
2 hour 19 minutes. The calculation is based on the bottom count curing second. Here that is 35 second, and 2 layer was there, and the rest was 10 second. So means if we divide that 3.2 mm to 0.01 layers, so it will be around 320 layers. 320 layers into 10 second will be the overall time of that slicing. If we save it, it will be in the .dlp format. So you can save it in any pen drive.
It is similar to the FDM case. We can also load the file on DLP and we can just quickly this your specimen. Okay. So I think it is fine because we don't have the power supply.
So we have USR.
Yes, it is connected with that?
Yes, sir.
First this correct. Keep it there also. So sir, these are the ranges actually. It comes with the water, right? This water. See, standardized, then it will be. So the cost of resin actually varies according to the material. So I think this one is 1000 rupees per liter or 2000 per liter. This one,
Which one?
the standard one.
Standard resin grade is 1800 only.
1800, na? Almost approx 2000 rupees per liter, right? Per bottle, not per liter, per bottle. And we also purchased one resin that was costing around 8000 rupees
Flexible
per bottle. Flexible resin, yes. And also one more resin we purchased that was not flexible, but that was
High temperature.
having the property
And sustain.
that was high temperature value.
That is PR300.
PR300. It was also around 8000 rupees per bottle. So the cost of the material can vary,
All thermoset resin.
right? Huh? हाँ.
Bottle.
हाँ, लगा लिखा है. Everything is mentioned there.
This is the flexible resin.
And this is flexible resin which we have the handy record for some purpose, right? So one is the company 3D Hydrotrack. This is a very famous company. So they can supply the material as per your requirement. So in their catalog you can find the suitable material and you can order. Right? Told you that this specimen. So this we have printed by using this material, right? Flexible one. So we can just bind it and we can again regain what you said after binding also. So if you looking forward toward the 4D printing application, you know 4D printing? Anybody knows 4D printing? Expect this all because they are doing their research in 3D printing, right? So they know about 4D printing, but anybody? No? 4D printing? Have you heard 4D printing? Actually 4D basically is one additional dimension apart from 3D. Time is the dimension, right? With respect to time, material or the specimen will change its own shape under the applied stimulus. Suppose here I am applying this force here, okay? So now its shape has been changed and I can use it just for some purpose, for some application. But after a certain period of time, it will regain. Or if I apply stimulus, it will regain its shape. Okay? So you can just refer good articles on 4D printing. So this flexible material can help you. Right? To enhance the shape recovery characteristics of the specimens. Shape recovery is one of the key parameters for 4D printing applications. Okay. We need to deposit two different materials, right? So if I opt this DLP, I will not able to make these kind of specimens, or I will not be able to those specimens for electronic applications. So that is why we have developed the setups which can deposit two different materials, right? Which can give us these kind of parts for possible electronic applications. Right?
So in the DLP 3D printer, how to install means how to start the process. Just take the file from there. It will be in the .dlp format. So we take the pen drive and we insert it in the 3D printer.
Speak loudly. Speak loudly so that your voice can be heard.
Okay. So after the putting the file in the machine, we have to fill the tub with the required material we want to print. Right now this is the flexible material, flexible epoxy material that we have shown there. So this is the material we have filled. We have to fill it at a certain level so that means if the large part is there, material means won't be there, means shortage of material won't be there. So we have to fill at certain level. After filling the vat with the required material,
I think software gives the amount of material required for the printing.
last time we had
कल दिखा दो, बाद में कल लेना, कल दिखाते हैं। अच्छा दिखा दो।
So this is the vat. We can remove it from here. Just means to clean the vat. If you have to clean the vat, means if we have to change the material, we need to clean the vat also. So we can remove that vat from here with these screws. We have to wash the that vat with the that is chemical is there. The chemical we have that chemical. That is IPA, isopropylene alcohol is a chemical name. We can wash.
Whenever you want to change the material, you can change it, but first you need to wash the tank, right? By using this chemical only. Then you can pour the second material. Otherwise, it will react, right? It may change the property.
You have to use gloves also while handling
these UV materials.
This machine. So. Earlier the material was prepared for isopropylene. You can clean the material with isopropylene, but right now they are making material you can use with water also, so that it will be friendly to humans. Otherwise this material if you pour on your hand it will react also sometimes.
So this technique actually became popular I think during last 10 years only, right? Earlier the machines were not available in India. Low cost machines. Earlier SLA was there, that was very costly, right? But now it has become very popular, and almost that's why more materials are coming in the market. Now people are developing. In India also one of the company in Pune, they are making materials, customized materials. Suppose you want to develop a composite material for this composite resin for this DLP, they will prepare for you. So some companies are coming, some startups are coming. So in the next coming 5 years, you will see the vast range of materials that will be available for the use in DLP. But it will take time, right? Because currently we are procuring all the materials from China only, I think. Suppose, see, right? We are procuring the material from China. Then here suppliers are available. They are just supplying the pen India. All are procuring from the China.
So means that process that I have shown. You have to load the file .dlp file, and you have to put the resin in the vat. Then after that you have to clean the platform. This platform is there. You need to clean it so that the material gets stick after UV light will fall from the bottom. The UV source is there.
UV light at the bottom, right? So when it will means switch on, this area will be exposed under the UV light, and we have already prepared the program, so that will only switch on that particular selective region only. For the selective region only, right? So that material will be cured automatically.
In the SLA process, if you know SLA process, it is a kind of laser kind of process. Means laser will fall and the curing will take place at the track. But DLP, single time whole layer will be get cured. Like UV light is projected on a surface area, the whole area get cured.
At a time, single layer is formed. At a time. But in FDM, what we were doing, we were just making the whole layer by depositing the material in the form of patterns. Similarly, in SLA, lithography, we have the laser-based energy source, UV light. So it scans the whole layer by just moving along X and Y direction. But here we have projector, so that is switched on, right? So at a time, single layer is formed.
So the UV light coming in the form of projector, and the intensity in the form of milliwatt, like 2 to 3 milliwatt per centimeter square. Intensity is low, and that platform and the bed is there. If you maintain a gap in between platform and bed is 0.01 mm, so the liquid will fill in between them. The liquid will fill in between them, and you put a projector, means UV light. You put a projector in the form of UV light. After coming in contact with the UV light, this material will get solidified.
Glass, right? You can come and see. We have transparent glass here, and you can also see the UV source. Please come here, one by one. You can see the working principle of DLP process, right? We have the UV source at bottom, then we have transparent glass, right? At the bottom of the tank we have transparent glass, then we have this built platform, right? So this is, I think, the idea behind the solidification. Okay.
If you look at this different textile based preform structures, we can have oven preforms, non-oven preforms, or knitted preforms, or braided preforms for composite applications. And in all these structures, the mechanical performance of all these structures is decided by the orientation of the yarns within these particular structures. So, as a composite researcher, you must be aware about these oven preforms, right? You must have seen these oven preforms. For example, we have here, as I showed you yesterday, this is the glass fabric preform. This is the two-dimensional fabric because it has only length and width dimension, and of course it has a certain thickness, but this thickness is, in comparison to this length and width dimension, is very, very small, and this thickness is, maximum thickness is just 2 times the yarn thickness, right? The constituent yarn thickness, and therefore only we have to use multiple layers of this particular this fabrics layers, so that we can get a desired thickness. So we can have different view structures. For example, here we have this is the plain oven fabric, this is the twill oven fabric. So we can have again different other view based on the requirements. So these are the knitted structures, non-oven structures, braided structures. So in braiding also we can have 2-dimensional braided structures and 3-dimensional braided structures. So in 2-dimensional braided structures, braiding के बारे में
We
आपको
have
कुछ
to-
idea
I
है?
think we have
Okay,
not-
so let me tell you that braiding is nothing but simply the intertwining of the yarns. Your shoelace is one of the braided product, right? And for the composites, we also produce the braided structures in so that braided structure may be
जैसे छोटी वो बनाते हैं
right. That is only. So it is the intertwining of the yarns, and we can have, this is the normal two-dimensional braid, and we can have 3D braid also. So in 3D braid, the yarns passes through the thickness, through the structure, and therefore we call it as a three-dimensional braided structure. These are some other structure as lace and net. So if you look at the as I said you that if you look at the mechanical performance of these textile structures, the mechanical performance is governed by orientation of these strands within the textile structure. So if you look at the reinforcements, for example this two-dimensional fabric. So in this particular case, we can see that the yarns are placed in the two directions, and this fabric is two-dimensional. It has length and width dimension only, and thickness dimension is very minimal, so we do not consider it, and we say that this is the two-dimensional structure. We can also have the preform, unidirectional preform also, where majority of the yarns in the only one direction, so that is called as unidirectional preform. The other structure is 2.5D. 2.5D, so all of you know the terry fabric, terry towels. So in the terry towels, the loops are standing on the fabric, right? So therefore we call it as a 2.5D
meaning of
fabric.
2.5D?
2.5D means here only the loops are standing on the
No, why we are calling them 2.5?
because it is in between 2D and 3D. Why it is in between? Because the loops, the loops which are only supported at the base are only are on the fabric, right, on the fabric surface, and
So can you show us
therefore,
any example or any?
so the terry fabric, the terry towel fabric, all of you
No.
seen the terry towels, right? Terry towels.
But do we have any sample of
Sample terry towel sample right now I don't have.
Normal face towels?
Bath towels.
Bath
Bath towels. You know the
That with okay,
Ah.
white tape.
right.
That the towel which we get in hotels.
Right. That is the terry towel.
Over the surface, you
The loops are
outside.
protruding from the
U-shaped
surface, right? So that is the terry towel fabric. So that is the example of 2.5D fabric, right? And 3D fabrics, 3D solid fabrics. So here the constituent yarns are disposed in 3 different directions to produce this 3-dimensional fabric. And as I told you that there are variety of 3-dimensional textile structures. So for example, if you look at the classification based on the type of 3D structure, we have 3D solid structure. For example, orthogonal, angle interlock and warp interlock type of a 3D solid structure. We can have 3D hollow with even surface and uneven surface. I will show you in the subsequent slides. We can have 3D shell structure. For example, we can produce a textile structure with shell. For example, the helmet, we can produce directly that type of fabric structure using the weaving machine. 3D nodal structures. So that will also, I will show you the pictures of the 3D nodal structure also, so that you can. Based on the process, we can have 3D oval structures, 3D metered structure, 3D blended or 3D non-oval structures. So these are the different textile structures, development processes: weaving, knitting, braiding, and non-oval. Based on the type of weaving machine, so we can produce this 2D weaving. You can use 2D weaving machine, normal weaving machine, to produce the 3D structures. We can have specialized 3D fabric manufacturing machine for the 3D fabrics, and another one technique is the looping technique. So if you look at the 3D fabrics, so as I said you that 3D fabrics have substantial thickness and the thickness is many times higher than the thickness of your constituent yarns. So if you look at this particular fabric structure, so you
So how
have
do
this.
you manufacture these fabric? Means what is the procedure to manufacture?
So I will discuss the procedure also in subsequent slide how to manufacture these structures. So if you look at this particular picture, you can see that the thickness substantially higher thickness, and I have already shown you the 3D fabric yesterday. So this is the three-dimensional orthogonal fabric. This is the solid structure, and it has 4 layers, 4 stopper layers, 5 weft layer. So total 9 layers are there, and we have this integrally woven 3D orthogonal structure. In comparison to this is made up of jute yarn. This is the jute yarn. Similarly, you see the same yarn we have used to produce this 2D plain view fabric, and you can see that thickness is only 2 times the yarn thickness, but here we can get a substantially thicker fabric just because of this particular typical structure of this particular fabric. Now in case of this particular 3D fabrics, 3D solid structures, there are, as I discussed with you, that there are 3 different solid structures. One is 3D orthogonal structure, another one is 3D angle interlock, and third one is a 3D warp interlock or layer to layer interlock. So in orthogonal structure means where the 3 different sets of yarns are perpendicular to each other. If you look at this simple 2D fabric, in this case you have only 2 sets of yarns. See, this is the one vertical set of yarns and another one is the horizontal sets of yarns, right? Only one vertical set of yarn and another one is the horizontal set of yarns, which we call warp and weft. Only 2 sets of yarns. But in case of our 3D solid structures, we have 3 sets of yarns. So one is moving in the warp direction, the another one is in the weft direction, and the third set of yarn which binds these layers of the yarns, which is called as binder yarn. And in orthogonal structure, this binder and the warp and weft, they are mutually perpendicular to each other, and therefore we call this type of solid 3D structure as a orthogonal structure. And this is the example of this 3D solid structure. So in this is the repeat unit, and we have shown here the cross section of this unit, and you can see the only one binder. But if you look at this particular fabric, across the width of the fabric, we can have multiple binder yarns. More is the binding, we can have more stiffer structure. In case of angle interlock structure, the binder moves through the structure. It goes through the structure from the one side of the fabric to the other side of the fabric, and again on the surface, from the surface to the back, again to the surface, and it moves through the thickness of the fabric at certain angle. If you look at the layer to layer interlock, here different layers are interlocked with the help of binder. So if you look at the structurally, if you look at this particular 3 different structures, you will understand that this particular structure, orthogonal structure, is more stiffer compared to your angle interlock and warp interlock structure. And this is the reason why we have to use angle interlock and warp interlock 3D preforms for composite materials having some complex shapes or maybe curved shapes, where you can easily bend in this particular preform structure in that particular shape. Whereas bending this particular structure, you see that This is very stiff structure. So bending according to that particular shape is very difficult. This is with the this structure is made with the jute. If you make it with the carbon or glass, it will become more stiffer. And bending this particular structure will become very, very difficult. Right. So therefore, in that case, we have to use angle interlock or warp interlock type of a structure. And so we have discussed the limitations of these particular structures also. Coming to the hollow structures. So we can have, as I said that in the classification, we can have the spacer structures connected with the core piles, spacer structures connected with oven crosslinks. Then we can classify them as spacer structures with even surface and spacer structures with uneven surface. For example, this is the honeycomb structure where the surface is not even, right? Whereas in case of this particular spacer structure, the surface is even. So, in case of this, so this is the example of spacer structure with uneven surfaces. So look at this honeycomb structure. Now, the next important aspect of this particular study is how to produce these particular structures. Right. Before going further, let me discuss how to produce these particular structures. So, to produce these particular structures, we need specialized weaving machine for that. Right? For example, if you want to produce, let's say, this type of a structure, spacer structure connected with the oven crosslink, or this spacer structure connected with the core pile, or maybe this honeycomb type of structure, we need a specialized weaving machine for that. And this particular specialized weaving machine should be equipped with, you can say, arrangement to accommodate multiple number of warp sheets or the yarn sheets. For example, here you see you have multiple layers of the yarns, and there should be arrangement to accommodate these multiple layers of the yarns. Further, you should have, so again, these are the, I cannot go in more detail about the weaving machine because it will be difficult for you to understand, but I will show you the weaving machine, one weaving machine which we have in our lab, where I will try to explain you that these particular structures, how to produce this particular type of a structure using this particular the available weaving machine in the today's situation. Because if you look at manufacturing of the 3D oven fabrics commercially is very costly. Why? Because if you want to produce such type of structures, 3D oven structures, what happens is that since you have to insert number of wefts as per your requirement, and it will reduce the production speed. It will reduce the production, and therefore it becomes very, very costly. And again, one more thing is that if you want to switch from the one structure to other structure, for example, a particular loom can only weave solid structures. You cannot use that particular loom to produce hollow structures. So you should have a separate type of a weaving machine. Loom needs weaving machine to produce the solid structure. You need a separate machine to produce these hollow structures. So this is the again one 3D structure, that is 3D shell structure. So in this particular case, we can produce the shell type of a structure directly on the weaving machine by changing the fabric take up rate. At what rate you are taking up the fabric? If you change at different places. So you can get shapes like this, and you can directly use these particular shapes and impregnate the matrix material in that particular shape, and you can get a composite material according to that shape. So this is the nodal structure. This is the 3D oval nodal structure, where such nodal network you can produce directly by weaving on the loop, and you can convert these particular structures in the composite form. So let me show you one. So this is the one of the 3D weaving machine, right? So if you look at this particular machine, you have here a creel zone where we have to place the yarn packages. So yarn, maybe so this is the glass yarn, you can have carbon yarn, right, or basalt yarn, for example. So this is the creel zone, and from there we have to take it, this particular yarns, and it will be passed through some machine components. For example, you have the hilled wires, hilled frames, and the reel, and then it will be taken to this take-up zone, and these structures are produced. And you see this. These are some of the examples of the 3D fabrics. So here, depending upon how much is the thickness, so we have to produce the 3D fabric with those many number of layers in that particular 3D fabric. So for example, you see that here you have 1, 2, 3, 4, 5 layers, 6 layers, sorry, 6 layers of the warp. So, and here you have to insert the weft yarn, the horizontal set of yarns, and in this particular opened shades to produce these particular different types of 3D solid structures. This is again the 3D spacer structure, and again to produce these particular 3D spacer structures we need a specialized weaving machine with special mechanism. Again, in case of honeycomb structures, we can have honeycombs with different cross-sectional shapes, and to produce these particular structures, what is required is in detail knowledge of the weaving technology. Detailed knowledge of the weaving technology is very much essential to produce these textile preform structures. And as we have discussed yesterday, that this preform structure largely governs the mechanical performance of the composite material. At the same time, it decides the life of this particular composite material also. For example, we have yesterday discussed that, let's say we have this laminated composite, which is very, very famous, where multiple layers of 20 fabrics are stuck together, and we impregnate these layers with the matrix material. But what happens with this particular type of laminated composites? It delaminates under various loads during the application of this composite material, and it will lead to the failure of the composite material, entire composite material. So that's why we can have this, to avoid this delamination, we can have this 3D integrally woven structures like this, where there will be no delamination, and the mechanical performance will be enhanced many times. At the same time, the life of this composite material will be again enhanced just because of this particular preform structure, right? So that's all about this particular 3D structures, and I will show you one prototype weaving machine which we have fabricated. so that you will understand how the fabric weaving is done. Right?
Sir, I have one small doubt.
Please.
We are evaluating the mechanical performance of these fabrics, but can we consider the thermal aspect? Because whenever we are doing the exercise in the morning session, so our body gets hot, and in order to maintain the thermal equilibrium in the surrounding, we need to dissipate the heat. So nowadays I have referred to articles where the conductive fabrics are there. So what will be the role of this conductive fabrics and whether it will have any impact on our health? Because this is very emerging.
So, of course, but conductive fabrics and these things are different. These 3D fabrics are developed only to produce the composites for structural application, and they are not used for apparel applications. These are specifically produced to develop structural composite materials. Structural means load-bearing composite materials, right? And they're not for the apparel application, right? Any other query if you have? ठीक है? Okay.